Hello, and welcome back to Shiksha. So today we're going to talk about quadratic and exponential relations. In this lesson, you're going to learn how to tell the direction of a parabola just from its equation. We're also going to explore a little bit about what does it mean when an exponent is not positive, and then we're going to compare the graphs of x squared and y equals 2 to the power of x. To start off, think about this inequality right here. When you have ax squared is greater than 0, in other words, when is a times x a positive number? When is it greater than 0? Think about what does a and what does x have to be in order for this inequality to be true. Pause the video here and see if you can come up with a rationale yourself. Well, hopefully one of the things you realize is there are three numbers here, and they are all being multiplied. And one thing to keep in mind is when we're looking for the positivity or negativity of a product, we know that when we're multiplying two numbers together, if one of them is negative, their product will be negative. But if both are negative, or if both are positive, the product will be a positive number. So there are only two variables here, a and x. Let's see if we can make a little chart. What happens if a is positive? What happens if a is negative? And then for each situation, what happens if x is positive or negative? Looking at this one here first. If a was a positive number and x was a positive number, then you would have a positive times a positive times a positive. So here I have an orange a and in blue x times x. That's x squared. Hopefully you realize that, okay, well, if I'm multiplying three positive numbers together, I should get a positive number. So one of the things that needs to be true for ax, or one of the ways that ax squared could be greater than 0, is if a and x are both positive. Well, what if x is negative? Well, in that case, that would be a positive times a negative times a negative. And remember that two negatives, when you multiply them, they actually give you a positive. So these two right here would be a positive number. And then if I multiply that by a positive number, I should get a positive number at the end. So even if x is a negative number, ax squared can still be positive if a is positive. And if a is negative, though, then we've got a negative number times two positives. A negative times a positive is negative, so these first two are negative. And then if I multiply that by a positive, again, we have a negative times a positive. So that gives us a negative number. Notice that x squared, if x was greater than 0 or less than 0, x squared always ended up being a positive number. So if we take a positive number and we multiply it by a negative, we'll get a negative. And in fact, even if we take two negative numbers and we multiply them together, we will get a positive. So we're in the same situation where a positive times a negative always gives us a negative. So to summarize what we're looking at here so far, and hopefully you recognize that these are the only conditions for when ax squared can be greater than 0. The idea here is, looking at the value x squared, it doesn't matter if x is negative or it's positive. These two multiplied together, because they do represent the same number, the answer will always be positive, unless it's 0, but then the whole product would be 0. And if we're taking a positive, if x squared is always going to be positive, and then we multiply that by a, well, then really the only thing that affects the positivity and negativity is a. It's either going to be negative if a is negative, or it's going to be positive if a is positive. In this investigation, we're going to compare three graphs. We're going to say, what might the graphs of y equals x squared, y equals negative x squared, and y equals 2 to the power of x look like? Now, when we're looking at y equals x squared, the easiest point to plot is, of course, the point at the origin. When x is 0, 0 squared is equal to 0. So 0, 0 is one of those coordinates. And we know that if we multiply a number by itself, the bigger that number is, the greater their product will be. And so the right side of the number line, as x increases, y is going to increase not linearly, but in a quadratic manner. It's going to increase faster and faster and faster. And as we saw, when we decrease the value of x, because this is x squared, a negative times a negative will always be a positive, and these will therefore be positive as well. Moving on to negative x squared, something very similar will happen. It still has a point at the origin, right? Negative 0 squared is still equal to 0. But then as we increase the x value, the x squared ends up being a big positive number, but then we are making it negative with this negative over here. So we're multiplying it by -1. And that's going to take the exact shape, and it's going to make all of these y values negative. So they will actually be underneath the x-axis. And if we go negatively, a negative number being squared is a positive, and then this negative in front will make it right back to being negative. So as x decreases, the y values increase quicker and quicker, but then this negative in front turns them all into their negative opposites. Negative opposites, is that a thing? I don't know. We're making things up now. Now let's take a look at the graph of y equals 2 to the power of x. Notice that this is very similar, but the x and the 2 have swapped places. Is that also going to create a parabola? Pause the video here and see if you can answer that for yourself, if you think it's going to create a parabola or not. Before we actually start to graph it, let's take a look at what 2 to the power of x, what the table of values for that might look like. To understand what happens when an exponent is 0, or even when it's negative, take a look at these tables of values here. As the exponents increase, so as we go from 2 to the power of 1 to 2 to the power of 2, and so on and so forth, notice that every time you should know this by now, but every time you increase the exponent by 1, you're multiplying by the base once more. So this is 2, and then 2 to the power of 2 means 2 times itself, 2 times. So 2 times 2, and that gives us 4. What does 2 to the power of 3 mean? It means 2 times 2 times 2 again. 2 multiplied by itself 3 times, and that gives us a total of 8. If we're increasing it by 1, we'll multiply by 2 again to get 16, and then again to get 32, and then again to get 64, and we could keep going. And if increasing the exponent means that we have to multiply by the base once more, well then what does decreasing the exponent do? Pause the video here and see if you can figure that out for yourself. What do you think would happen if we were to decrease this exponent? Well, hopefully you realize that, well, if this means multiply, then the opposite direction probably means divide. And yes, in fact, decreasing from 6 to 5 means going from 64 to 32, which we can accomplish by dividing by 2. And similarly, 32 to 16, dividing that by 2. 16 to 8, dividing by 2 again. Down by 2 again. Down dividing by 2 one more time. And so if we are going in this direction and decreasing the exponent, well then what if we didn't stop at 2 to the power of 1? What if we kept going to 2 to the power of 0? Well, this pattern I would think would continue. And if we take 2 and we divide it by 2, we get 1. So 2 to the power of 0 actually is equal to exactly 1. And we don't even have to stop here. We can keep going. We can keep going even lower to the negatives, to the integers. And this pattern would keep going. So 1 divided by 2 is 1 over 2. 1 over 2 divided by 2 is 1 over 4. Divided by 2 is 1 over 8. Divided by 2 is 1 over 16. So here are some powers of 2, including the 0th power and some negative powers. Let's see if a similar thing will happen when we look at the powers of 3. So if we start at 3 and we increase the exponents, that means we're multiplying by 3 again, 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 however many times the exponent tells us to. So right now I've got 3 to the power of 6. That means 3 times 3 times 3 times 3 times 3 times 3. A total of 6 3's being multiplied together to get us 729. And yes, to go in the opposite direction, of course, we would divide by 3 again and again and again and again. And just like with 2, we don't have to stop here. We can say 3 to the power of 0 is 3 divided by 3, which is just 1. Anytime you divide a number by itself, you always get 1. And if we want to go into the negatives, 1 divided by 3 is 1/3. A third divided by 3 is 1/9. A ninth divided by 3 is 1/27th. And a 27th divided by 3 is 1/81st. And so now that we're done looking at this with a few tables, let's extrapolate this idea to any power no matter what the base is. So here, x to the power of 1, that's like saying, hey, we just got 1x. And if we increase the exponent to 2, now x times x gives us x squared. If we increase it to 3, well, we should end up with x cubed, x times x times x. Once more, x to the power of 4. And we can keep going as long as we want for whatever this exponent will be. It's always x times itself n times. And very similarly to 2 and the powers of 2 and 3, when we're decreasing the exponent, we can divide by x. So this will reduce the exponent by 1 until we get all the way back to where we started. So 4x to the power of 4 divided by x is x to the power of 3. The exponent dropped by 1. Divided by x again gives us x squared. Divided by x again gives us x to the power of 1, which is just x. And if we go to x to the power of 0, we find out that, well, how do we get this? Well, if we start at x and we divide it by x, what do we end up with here? One thing to note is any number divided by itself is always equal to 1. And so no matter what x is, x to the power of 0 will be 1. And if we extend that idea down to the negatives, right, 1 divided by x is 1 over x. In the same way that 3 to the power of negative 1 was 1/3, 2 to the power of negative 1 was 1/2, x to the power of negative 1 is 1 over x. X to the power of negative 2, well, we just divide by x again and we get 1 over x squared. And we can keep doing that until we reach x to the power of negative n, which is whatever that number is. We know that that's going to be 1 over x to the power of positive n. So this is something to keep in mind here. We've learned 2 rules. One is that anything to the power of 0 is always equal to 1. And if we have if we have any base to the power of a negative exponent, we can turn that exponent positive just by taking the whole power and shoving it in the denominator, by taking the reciprocal of that power. So now let's take a look at what the graph of y equals 2 to the power of x looks like. Well, 2 to the power of 0, we know, is always going to be equal to 1. So our point here is slightly higher than it was here. And I know that every time I increase x by 1, I have to multiply by 2. If I increase the exponent to 1, to 2 to the power of 1, that gives me a value of 2. And every time I increase x by 1, the y value has to be multiplied by 2 again. And again. So 2 to the power of 3, which would be right here, 2 to the power of x when x is 3, is 2 times 2 times 2, which is 8. And I can see here that the y values are going to be increasing faster and faster and faster. And that looks very similar to the right arm of the quadratic here. But if I move to the left side, remember now I have to divide by 2. And so my numbers are going to get smaller. And then I'll divide by 2 again, and my numbers will get smaller than that. But they won't actually reach 0. Because if I'm always taking half of a number, well, or half of what's remaining, well, I'll never actually reduce it all the way down to 0. This behavior is called asymptotic behavior. It's when a relation gets closer and closer and closer to a number, but it never actually touches it. So here, as x is decreasing, the y values are approaching 0, but they'll never actually touch the x-axis. So what's the big deal with this lesson? To summarize it, basically, for any quadratic equation, y equals ax squared plus bx plus c, if the a value is positive, right? If a is feeling positive, what do you do when you're feeling positive? What does your mouth do? It smiles, it opens upwards. But if a is less than 0, if a is feeling negative, what do we do when we're negative? We frown, and the parabola would therefore open downwards. The other thing that we covered today is the meaning of 0 and negative exponents. Anything to the power of 0 is always equal to 1, and anything to the power of a negative exponent is equal to the reciprocal of that power with positive exponents. State whether the graph of the following quadratic relation opens upwards or downwards and explain how you know. Well, in this case, I know that if A is positive, the parabola opens upwards. If A is negative, the parabola opens downwards. And one thing to note here is if you find the second differences, these will match the sign of A. And now looking at my equation, because the value of A is -4, this parabola will open downwards, since -4 is less than 0. This parabola will therefore open downwards. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.